All right, so let's talk about the fluid. First of all, what is fluid? Something that can flow. So mainly, how many states of matter do you know? The solid, liquid,
And gas.
gas, plasma, stuff like that, right? So
Right.
so when you combine gas and liquid, both of them flow, right?
Yeah, they fill any space they're in.
Yeah. So that's why those fluid is the common name for gas and liquid. Okay, so gas is also fluid, liquid is also fluid. Okay, so in this chapter we'll be talking about fluid only. So before I go to the other property of fluid, let me refresh your memory by defining the mass density. Okay, so you already know that, right? So what is density? Density is mass per unit volume, right? Okay, so density rho. So this is, I don't know. So what do you call it? It's like a mirror image of 9 or something. Well, not quite, right? So this letter is this is a Greek letter, and we call it rho. R-H-O. Rho. Okay. So rho equals m over v, mass over volume. Okay, that's the density. So what is the unit, by the way? What is the unit of mass?
Kilograms
and volume is meter cubed, right? So that's the unit of density. All right, so this is the list of the density of some materials here. So, but in this chapter we'll be just talking about liquid and gas only. Okay, so you don't have to worry about this solid. In this book, well, we might need some density of related to solid also, but when we talk about liquid and gas, right? So we might need this also, but mainly we'll be focusing on liquid and gas. Okay, so this is just the table. Okay, now let's do one problem related to density. So blood as a fraction of body weight. So the blood of man whose weight is 690 Newton contains about 5.2 10 to the negative 3 meter cubed of blood. So find the blood's weight and express it as a percentage of body weight. So first of all, what is the mass of this blood? Do you know the mass of the blood? So if you, I don't think I have to explain too much here, right? So this is easy because your density is what? Your density equals mass over V, mass over V. If you divide both sides, multiply both sides by V, what do you get? If you multiply both sides by V, you get, so this V and V cancel out, right? Then M equals V0. Does it make sense? So mass of the blood is equal to volume of the blood and density of the blood. See, it's all blood. Mass of the blood equals to volume of the blood times density of the blood. So what is the volume of the blood here? Help me. 5.2 negative 3, that's the volume. So that's the volume, right? So what is the density? Well, I got it from previous slide. See here, blood. What is the density? It's written here.
10,060 kilograms per meter squared. Cubed.
So that's what I did here, okay? So you don't have to worry about this number because I always give you this value, okay? In the problem, I might not, but in the test, I always will. Okay, in the problem, you might have access to the book and everything, so I don't worry too much about it. But in the test, I'll definitely supply it. So if you multiply this together, you get 5.5. That's how you find the mass of the blood. Then how do you find the weight?
Converted to newtons?
Yes, so meaning weight is mg, right? You simply multiply by g and you get weight. So weight is 5.5 times 9.8, which is 54 Newton. You said it, yep. So 54 Newton. So first thing is done. Find the blood's weight. We did it. Weight is done. Now what is the part B? Express it as a percentage of body weight. So how do you do that? So what is the weight of this guy? What is the body of man whose weight is, see, his weight is this. 690 is his weight. And the weight of his blood only 54. Then what is the percentage of this, the weight of the blood? So 54 divided by 690 times 100. Does it make sense? So it is 7.8%. So 7.8% of the body weight is due to blood. Yep. Now let's talk about the pressure. So what is pressure? You already know this. Just, I want to refresh your memory again. So pressure is force per unit area. Suppose force is being acted on the area, on some area, right? This is a force is being acted on the area. If this area is unit, right? What is the total force acting on the unit area? Okay, in unit area means 1 meter squared. That's unit, right? So suppose the area is 1 meter squared, and you have some force acting on that area. Then what is that force? That force is called pressure. Meaning pressure is force per unit area. Does it make sense? So what is the unit of pressure? Pressure is, force is Newton and area is meter square. By the way, we can call it Pascal, okay? Newton per meter square is called also Pascal, which is PA. Okay, let's do one problem here. So force on a swimmer. So you see the swimmer in the on the slide, right? The guy is swimming there. So let's figure out the force on the swimmer. What is given? So the pressure acting on the back of the swimmer's hand. So we're just talking about hand here, back of the hand. So this area. Okay, we're talking about this area here. So if you zoom in, you see a little different, a little bigger here, right? So this is the area we're talking. That's the hand, back of the hand. On the back of the hand, what is the pressure acting on the back of the hand of the swimmer? 1.2 10 to the 5 Pascal. Okay. The surface area of the back of the hand is how much? This much.
8.4 times 10 to the negative 3 meters squared.
Thank you. Now, now what is the definition of, what is the formula for pressure? Pressure equals F over A, right? F over A. So can you, what do you know? You know the pressure, right? You know the pressure. You know the area. What do you need to find? Force. Okay, so how do you find the force? Help me. All right, so pressure times area, right? That's the force. So you multiply these numbers, you get the area. Done, right? How much do you get? If you multiply this together, you get 1 10 to the 3 Newton. Now, what is the next question we have to answer? Discuss the direction of the force. Look at this picture here and tell me the direction of the force. Look, on the back, what is the direction of the force? Downward. Downward, right? On the front part of your body, this is the front part, right? Front part of the body, the force is upward.
Up.
Back part of the body, force is downward. So which force you are talking about? Back of the swimmer's hand. Look, back of the swimmer's hand. Okay, so meaning what is the direction of the force? Down or up?
Down.
Down. Very good. Okay, so direction of the force is downward. All right, let's do the one simple calculation. I mean, let's figure out, derive a formula rather. Then we'll do one more, then problem also. Okay, we'll do the problem as well. So let's do this first. Okay, now what do you see here? You have a container which has water filled in, right? So now what you do here is inside the container, I take the hypothetical chunk of water. Do you see this hypothetical chunk of water here? So which is, you see the pink on the top and pink on the bottom? So
Mhm.
you see the top and the bottom part of the chunk, and you see this big chunk here, right? So this one. So what I'm trying to say here is, how is the pressure here, this point, and pressure here are related? That's what I'm trying to do now. Okay, I call this point 1, I call this point 1, I call this point 2. What is the pressure between 1 and 2? How are the pressure between 1 and 2 related? That's what I'm trying to do. So how many force do you see? So let's say we're talking about the force acting on this line. This line I'm supposed to make vertical, like here. Do you see it vertical? So in this direction, how many forces are being applied? One force due to the pressure. Suppose pressure on the top is P1, right? At this point, what is the pressure? P1. Then how do you find the force at this point? P1 times A. That's the force. At this point, the force is P1 times A. Does it make sense? So at this point, what is the force? Right at this point. At this point, what is the force? P2 times A. So why do I call same area? See the pink part here on the top and bottom? They're exactly same area, right? That's why I'm saying, they're equal and opposite, equal area. So let me repeat it. Force right here is P1A, which is acting downward, right?
Mm.
Okay. Force right here is acting up, because this guy is pushed in from all the side. Yes, you did hear it correctly. So this guy is pushed in from all the side, meaning from the top, from the bottom, from the side, from the front, from the back. So this guy is pushed in from all the side. Does it make sense? That's why. So we see this force acting down, this force acting up. Does it make sense? Then how about another force here? There is another force also. The weight of the chunk itself. So mass times gravity, right? Acceleration due to gravity, which is force. So there are 3 forces. One is P1A, the other one is P2A, the other one is mg.
Would P2A and P2 and P1A be related?
If they are related, that's what we are going to figure out.
Okay.
They are definitely related. That's what we are trying to do. Our goal is to relate them. Now, so all those forces are in the same line, right? But 2 of them is downward, the one is upward.
Mm.
Okay. So as you said in the beginning, they are in equilibrium.
Mm.
So equilibrium means what? Summation force equals 0. All the force equals 0. Net force is 0.
Mm.
So what are the net force here? What are the forces here? P1A, which is negative. Downward is negative, right?
Mm-hmm.
Mg, also downward, which is negative. Then what is P2A?
Positive because it's going up.
Exactly. So we have to add all these things together, which is 0. That's called equilibrium, as you said earlier. Okay. So P2A equals, if you take these 2 guys on the right hand side, both of them, P1A and mg, then what do you get? You get the relationship between P2A and P1A, which is P2A equals P1A plus mg. That's how P2A and P1A are related. Does it make sense?
Mm-hmm.
So what is your M here, by the way? What is the mass of this guy? This M, right? This M. What is this M?
We don't know.
We don't know, but can you relate in terms of volume and rho density? Mass is volume times rho.
Yeah.
Yes.
Okay, so I'm going to plug this in here. So I'm going to plug in the value of m here, which is b rho. Okay, so that's what I did here. So I did plug this in here, b and rho. Sorry, this one, b and rho. This is my mass. So I rewrote that in terms of density and volume. Now I'm rewriting my volume again. What is the volume of this chunk? I'm trying to replace this volume by something in terms of the height. So how do you relate the volume with the height of the chunk? Volume is area times height. Okay, so that's what I did here. So I did exactly rewrite this here, but I replaced by B by A times area times height. Does it make sense? So what happens if you divide everything by A? Right, left and right hand side by A.
Everything, all the A's would cancel out.
Exactly, you get P2 equals P1
P1 plus PHG.
Rho HG.
rho HG. Thank you. Yeah, rho HG. Okay.
What is it, rho?
Yeah, it looks like P, right? It's like yeah, this is called rho. RHO.
Oh,
Okay.
rho.
Rho. R.
RHO.
Oh.
ROH.
RHO. That's the rho. Okay.
Rho.
So
Okay.
P2 equals P1 plus rho HG. Okay, that's the formula we derive now. So this is very useful formula. Okay, it will be given given to you in the test. Okay, I'll give this to you, but just in case you are wondering how you got this formula, this is what we did so far. So P2 equals, P2 is, remember this P2 is the bottom point. Now keep this in mind. P2 is the point here, bottom point. Okay, and P1 is the top point. Bottom equals top plus rho HG. All right, let's do one problem then. There is a swimming hole. Points A and B are located at a distance 5.5 meter beneath the surface of water. Find the pressure at each of these two locations. Okay, this A prime, B is just like the sheet of paper. Okay, it's flat. What is the height of this guy from the surface? If you go downward, I'm talking a downward height. From the surface, you measure from the surface, downward height. What is the height? H.
5.5 meters.
Yep, 5.5. So now find the pressure at each of these two locations. So what is the pressure here? And what is the pressure here? What is the pressure on the top? This is just on the surface of the water, right?
Mm-hmm.
So that should be equal to the surface of the atmosphere. You know, the atmosphere around us. Okay, because that's the atmosphere, right? Our atmosphere is just touching the surface of water, right? It means at this point, the pressure is equal to atmospheric pressure. So how much is the atmospheric pressure? Do you know the value? Is constant, okay? It will be given in the test. The atmospheric value is this one here. Do you see that? 1.01 10 to the 5 Pascal. That's called atmospheric pressure. That's the pressure at this point here, right here. One question is already answered. Now, next question is, what is the pressure here? We need to figure that out. Remember, we had the formula, this formula here, exactly this formula. We are going to use this formula now, this formula. P2, which is the bottom, right? Bottom on the, pressure on the bottom is equal to pressure on the top plus rho Hg. That's the formula we are going to use here. So do you know the pressure on the top? P1. That's the constant. Okay. So that's what it is here, right here. Then what is rho? What is the density of water? 1000, right? This is 1000. What is the G? Obviously, you know this, which is 9.8. What is the H?
5.5.
5.5. If you multiply all together and add this to this guy, then you get 1.55 10 to the 5 Pascal. So we are done with this problem now. Okay, Now I'm going to use that formula again. Remember this formula again. This is very, very important. That's why I derived this also, right? We know how we derive this, right? How to derive this. So, but in the test, you don't have to derive it. It will be given to you. Now P2 equals P1 plus rho GH. Now, so do you know how the pressure gauge work?
Mm-hmm.
So this is how it works. Like this is the mercury, right? And you see the height of the mercury here. So this is the very small tube, right? Very, very little tiny tube, like, I don't know, it's like needle shape, I would say, okay? The tube is very tiny, just like needle, okay? So this is the needle shaped tube, and if you fill this tube by mercury, right? And place it on the container which has also mercury, then what happens is, even though it was full in the beginning, it is completely filled here, up to here, okay, up to here, completely filled. Depending on the height of the place where you do the experiment, this height will vary. In some places, this will have this height. In some places, you will have this height. Some places you will have this height. Depending on the place where you are measuring the pressure, atmospheric pressure, you know, it will be different. But if you are talking about the pressure on the sea level, you know that number, right? That number is this. On the sea level, this is the pressure. But for simplicity in the test, when I say atmospheric pressure, you know, even in Plattsburgh, right? It's the same value we use. Okay, it doesn't, because we are very near to sea, so it's tiny variation. We just disregard it. Okay, we simply take that value. Okay, so now at this point, you feel the mercury in the beginning, but the mercury itself goes down depending on the pressure of that particular place. Now, when the mercury goes down, now you can simply call this empty, right? There's nothing is there. Mercury was there in the beginning, but now nothing is there. Means it's vacant. It's vacant. Not even air. Does it make sense? Then what is the pressure of this portion of this of the tube? What is the pressure inside this part of the tube? It's exactly 0. Does it make sense?
Mm-hmm.
I have a question here. P1 is 0 because in the beginning the tube was full, right? Now, depending on the place where you do this experiment, you will see the decrease in the height of the mercury on the tube. So now when the mercury goes down, this space is empty, right? This part is empty. Empty meaning the pressure is 0. Does it make sense?
Mm-hmm.
So meaning in this case my P1 is 0. Then what are you left with? You are left with P2 equals rho GH. By the way, that P2 is called atmospheric pressure.
Mm-hmm.
That P2 is called atmospheric pressure. Now, in the real life, this is what we do. So, is this rho constant? Rho is the density of mercury. What is G? 9.8.
Yeah.
So, what is H? That's the thing only varies, right? Depending on where you do this experiment, you will have different H. Okay? So, everything else is constant. That's why what people do is, instead of finding pressure, they simply find the height. Does it make sense? So if you talk about the pressure, they talk about, okay, 760 mm of Hg. Have you heard that? 760 mm of Hg, meaning Hg means the mercury. Okay? So they just talk about the height because of this reason. Because if you want to talk about pressure, only thing that matters is the height, because rho and G is constant. So how do you find the height? Height is P divided by rho and G, right? If you divide both sides by rho and G, you get height. That's what I did here. On the sea level, what is the height of this barometer, this pressure gauge? So on the sea level, you know your P, right? Which is 1.1 10 to the 1.01 10 to the 5. Then what is the rho? Rho, in this case, what is the material inside the tube? Help me here, please.
Mercury.
Mercury. So how much is the density of mercury?
13.
Yeah, if you go back here, I think I have it here. Look at this.
13.
Had it 13,600. Okay, that's the 13.6 10 to the 3. That's the rho, density of mercury. Then G, obviously you know that, right? 9.8. Then if you want, if you do this calculation, you happen to get 0.76 meter, or people normally talk this in millimeter. That's why I decided to change this to millimeter. So on the sea level, the atmospheric pressure is 760 mm of Hg. Or you can say simply 1.01 10 to the 5 Pascal. It's the same thing. Mm of Hg, meaning you are talking about the height only, because you are ignoring rho and G, because you know they are constant, right? So why bother talking again and again? That is constant. So some people think that way, and some people just give you the total value, simply 1.01 10 to the 5. But this is this is the SI unit. When you do the calculation, you have to use this value. Okay, this is just for in everyday life. This is the language for the everyday life. But when you do the calculation, you have to use this exact value. Does it make sense? Okay, now I'm going to do the Archimedes principle. So buoyant force, this B is buoyant, okay? So buoyant force. So here, remember this buoyant force. This B is called buoyant force, okay, by the way. This is FB, I call it FB, okay. So what is the buoyant force? Buoyant force is the upward force acting on the something that is on water. Let's say fluid, any fluid. In this case, let me consider this guy, this cylinder is filled with water, and I have something in it. This guy is something inside the water. Okay. Now I'm trying to find the buoyant force. As I said earlier, this guy has force all around it, right? All around it. From the side, from the top, from the bottom, right? But you might have a question here. Why are you just considering top and bottom only, right? You are considering top and bottom only. How about sideways force, right? Why are you ignoring that? You might have a question there. There is force, then why do you ignore, right? The answer is because they are sideways, so they all cancel each other. This force cancel with this force, and other force here at this location cancel with this force. The force right here is cancelled with this force. Okay, so there is always a counterpart from left and right. That's why they cancel each other. That's why we don't have to talk about the sidewise force. Just you have to talk about up and down. Does it make sense?
Mm.
Okay. Now, what is the buoyant force? Mean upward force. Remember, this force is bigger than this force, right? Because remember, bottom is bigger than top. You already found that. See that?
Mm.
See, the bottom is bigger than top, because if you add this guy to the top, then you get bottom. Does it make sense? Meaning bottom is bigger than the top. Okay. Now what happens if you subtract bottom and top? That's what I'm doing here. Because bottom is always bigger, you know that. So if you subtract the top one from the bottom force, then you get this. P2A minus P1A, right? So by the way, is the top area and the bottom area the same? See that? This looks circular here, and exactly the bottom is also circular. If the area of the top part is A, the area of the bottom part is also A. Okay? So both of them are A, same A. So they're same. That's why I just take it out. If you distribute A throughout, then you get exactly same thing again. Does it make sense?
Mm-hmm.
Okay. Now, so what is this guy? Can I call this the rho GH? Because how are the P2? What is P2 minus P2A minus P1A? Rho GH? We know that, right? Because P2 equals P1 plus rho GH, meaning P2 minus P1 equals rho GH. That's why I did plug this in here. P2 minus P1 is rho GH. Look at that. Then this A is A, rho GHA. So can I call this this A and H? What is A and H? If you multiply A and H, what do you get? Area times height.
Volume.
Volume, right? So that's what I did. Rho, G, and volume. Rho is the density of water. That's why density of water times B is the volume of this guy. That's what I meant. Volume of this guy, this guy in which is inside the water. So can you say the volume of the immersed object is equal to the volume of the displaced water? What I meant is when you dip submerge something into water, right? Then that guy will displace exactly the same amount of volume. Meaning volume of this guy is equal to volume of the water displaced by that guy. Okay, even though this volume is mass volume of the solid object here, this object, this is the volume of that object, but that happens to be equal to the volume of the water displaced. That's why we can call rho times B is the mass of the displaced water. There. This is the formula for buoyant force. Rho B G is the buoyant force. Rho, density of water or whatever fluid is. V, volume of the something that is into the water. In this case, that something is this guy. And that happens to be equal to volume of water displaced by that guy. Then you multiply by G. That's the formula for buoyant force. Let's formally state the Archimedes principle. Suppose we have a fluid and an object is either partially or completely immersed in it. Okay, there could be two situations. In this fluid, the object is completely immersed like this, or it can be other situation where object is partially immersed. Okay, then in either of those cases, the magnitude of buoyant force equals the weight of the fluid that object displaces. Okay, so the upward force, buoyant force is the upward force. This is the upward force or buoyant force acting on the object. Okay, buoyant force. That buoyant force equal to the weight of the fluid that object displaces. In this case, volume of the fluid displaced by the object is the volume of the object itself. However, in this case, volume of the fluid displaced by the object is equal to this immersed part of the volume. Specifically, when the object is floating, then the buoyant force can be also equal to magnitude of its weight itself. Okay, so this statement is general. Okay, this equal to that. Buoyant force equal to the weight of the displaced fluid is in general. Okay, in general case, meaning when the object is either partially or completely immersed, that's the general case. If the object is floating, then we can modify this Archimedes principle by this. Not only buoyant force equal to weight of the fluid displaced, but that equal to the magnitude of the weight of the object that is floating on the fluid. Okay, let's do a problem here. In figure, a block of density rho equals 800 kilogram per meter cube floats face down in a fluid of density rho f equals 1200 kilogram per meter cubed. The block has a height of big H equals 6 centimeter. So this block has the height of 6 centimeter, which is H equals 6 centimeter here. Now we are supposed to find the depth H. By what depth H is the block submerged? So we have to find this little h here, meaning the block is not completely submerged. Only part of it is submerged. So that part is big, little h, and the total height is big H. We need to find this little h. That's what we need to figure out. First of all, let's find the buoyant force. What is the buoyant force? Buoyant force is FB equals weight of the displaced fluid, right? Weight of the displaced fluid. This is Archimedes principle, right? So how do you find the weight of the displaced fluid? mf times g. We know rho equals mf over b, where b is volume of the displaced fluid. Volume of the displaced fluid. If you multiply both sides by b, this b and b cancel out. mf equals volume of the displaced fluid times rho. So what is the volume of the displaced fluid? Length times width times little h, right? Length times width times little h. That's the volume of the displaced fluid. Then rho, then g. So why little h? Because only little h displaces fluid, not the big H. So this is rho f, right? So what is the weight of the block? Fg equals mg, right? Okay, where m is b times rho. But in this case, we are talking about the entire mass, because we are talking about the weight of the block. That's why it is entire mass. That's why we have to have the entire volume. Not the volume defined by little h, but the volume defined by big H. So LW big H rho g. Since this guy is floating, so the net force is 0, meaning it's not, there is no vertical motion, meaning these two forces are equal and opposite, right? Fb equals Fg. It means LW little h rho Fg equals LW big H rho g. So multiply, so divide both sides by LWG. LWG, GG cancel out. Similarly here, these all cancel out. You are left with little h equals, if you also divide by rho f on both sides, then you have little h equals h times rho over rho f. Okay. So what is your h? H is 6. What is your rho? Rho is 800. What is your rho f? 1200. So if you multiply this, then you end up getting 4 centimeter. Okay, let's do one more problem here. A swimming raft. The raft is made of solid square pine wood. Determine whether the raft floats in water, and if it floats, how much of the raft is beneath the surface. We have two parts here. Determine whether the raft floats in water, part 1. If it does, then how much of the raft is beneath the surface? These are the two parts. So first of all, let's figure out whether the pine wood floats or not. Okay. If the pine wood floats, then the upward force, which is buoyant force, is equal to the downward force, which is gravity, right? If the magnitude of the buoyant force is equal to the magnitude of the gravity, then the raft floats, right? So let's find out how much is the buoyant force. Let's find the maximum buoyant force that the fluid can offer. Okay, so how do you find the maximum buoyant force? Yeah, B max equals the maximum water displaced by the boat, right? Maximum weight of the fluid displaced by the boat. So what is that? Which is rho water, B water, and G, right? So what is the volume, maximum volume of the water that could possibly be displaced? So that's how you figure out the buoyant force, right? So what is the maximum volume of the water? You have 4, 4, and 0.3. Okay, so what is that? If you multiply 4 times 4 times 0.3, you end up getting 4.8 meter cubed. That's the volume, maximum volume of the water that could be displaced. Okay, so raw water, which is 1000, right? Then what is the volume of water? 4.8, and density of water and acceleration due to gravity is 9.8. If you multiply that together, you end up getting 4700 Newton. Okay, that is the maximum buoyant force that we can have. This is the maximum possible buoyant force that the fluid can offer to the raft. If the maximum possible buoyant force is equal to the weight of the raft, then the raft will float. Let's see how much is the weight of the raft. Weight of the raft is equal to mass of the raft times gravity, right? So how do you find the mass of the raft? Okay, so density equals mass over volume. So from here, you can find mass equals rho times B. So you know the rho of the raft, which is pine, right? So raft is made of pine. So the rho of pine will be provided in the test, which is 550 kilogram per meter cubed. Okay, so let's plug this in here. So rho times B, right? 550. Okay, then B, then G. Okay, so what is the volume? Volume is, again, is the this one, these three multiplied together, right? So 550 times 4 times 4 times 0.3 times 9.8. Okay, if you multiply this together, you end up getting 26000 Newton. So in the previous case, what we got is maximum buoyant force that could possibly that the fluid possibly could offer is 47,000 Newton. Okay, this is big enough to support the weight. Okay, that's why, what is the conclusion? The raft floats. Oops, the raft floats. This is the maximum buoyant force that the fluid could possibly offer to the raft, but it doesn't have to offer this much buoyant force. So the buoyant force that is required to support the raft is this much only. It means the entire raft does not have to be submerged in the fluid, because when the entire raft is submerged, then you get the maximum buoyant force. Since we don't need the entire buoyant force, we need this much only. It means the raft does not have to be completely submerged, okay? So it has to submerge in such a way that it can offer this much force, okay? Then how much height is submerged then? Okay, let's figure that out. All right, so if the raft is floating, it means weight of the raft is equal to the buoyant force, right? So that's the Archimedes principle. So what is the weight of the raft? We know that already, 26,000 Newton. Then what is the buoyant force required for this amount of weight to hold? So what is the buoyant force? The weight of the displaced water, okay? So how much water has to be displaced? So how do you find the weight? Weight is mass times gravity. Mass is rho times B times G. Okay. What is rho of water? 1000. What is volume of the water? So you have this length, this is width, which is 4 times 4. But entire raft does not have to be submerged, right? That's why, let's say only H part that has to be submerged, okay? So that H part will displace the water. That's why we have the volume equals not the total height, but the small height, which is into the water, okay? That's the volume of the submerged part of the raft. Then we have G, which is 9.8, okay? If you do that, what do you get? So if you divide both sides by 1000 times 4 times 4 times 9.8 on both sides, 1000 4 times 4 times 9.8, then you got this cancel out here. Then you have H equals, if you do the calculation here, then you get 0.17 meter, okay? So it means out of 0.3 meter, only 0.17 meter has to be underneath water so that the buoyant force is enough to hold the raft. So now I'm going to talk about Pascal's principle. So what does Pascal's principle tell us? Any change in pressure applied to a completely enclosed fluid is transmitted undiminished to all parts of the fluid and enclosing walls. Suppose you have a pressure applied to this end of this enclosed fluid. This is completely enclosed in a tube here, as you can see. So this is the fluid enclosed. See the blue part? This is the fluid enclosed in a tube. Now, if you apply pressure here, okay, so then the same pressure is applied here, okay? So that's called Pascal's principle. So why is it important? I'm going to show you one example, then it will clarify the concept, okay? So let's do an example which uses Pascal's principle. So this is an example, a car lift, okay? This is a very interesting example. The input piston has a radius of this and the output plunger has a radius of this. So this piston has the radius, which is input, this. The output plunger has a radius of this, okay? This guy has a radius, this, okay? The combined weight of the car and the plunger is this. This is the weight here, 20,500 Newton. Suppose that input piston has negligible weight. This is negligible. And the bottom surface of the piston and plunger are at the same level. What is the required input force? So how much force is required here so that you can lift the huge car here? So even you can do it because you don't have to apply too much force because the Pascal principle will help you. Let's see how, Okay, so what is the Pascal principle? Pascal principle is P1 equals P2, right? Meaning pressure here, which is P1, is equal to pressure here, P2, right? So P1 is F1 over A1, right? What is P2? P2 is F2 over A2. All right. A1 is area of the input piston here. Okay, what is that? Pi r square, right? Which is circular. Piston is circular, which is pi r square. Pi times r is 0.012 square. So if you multiply this together, you will get some value here. Okay, what is A2? A2 is pi r square again, but your r is not different, 0.15 square. Okay, let's plug this in here. F1 over A1 pi 0.012 square equals F2 over this guy, right? Pi 0.15 square, right? Okay. Now the thing is, the combined weight of the car and plunger is given, meaning F2 is given. Since F2 is given, we need to find F1. If you multiply both sides by pi, then pi cancel out. Then you have F1, which is the force that you need to figure out. F1, this is the thing underneath, 0.012 squared. But F2 is given, right? F2 is this much, 20,500. That's the F2. And this is your 0.15 squared. So if you multiply both sides by 0.012 squared, right? So 0.012 squared, then this cancel out, then you end up getting F1 equals these three multiplied together. Okay, if you do that, you end up getting 131 Newton. Okay, look at that, the beauty of Pascal's law. If you want to lift the car of weight this much, then you just need 131 Newton force. Okay, so because the Pascal principle says that P1 equals P2, with the help of that, so we can easily lift the car. So meaning this much heavy car can be lifted by using this much small force, meaning 131 Newton force is enough to lift the heavy car having this weight. Okay, that's the beauty of Pascal's principle. Before I conclude this chapter, I'm going to talk about the equation of continuity. Okay, this is a very important concept. Before I jump into the equation of continuity, I'm going to define a quantity, which is mass flow rate. The mass flow rate is the mass of the fluid per second that flows through a tube. Okay, so in 1 second, how much kilogram mass is flowing through this tube? Let's say you have a container here. In 1 second, how much fluid is passing through this tube? How do you find that? So in 1 second, how much liquid is collected here? In 1 second, how much liquid is collected here is the same thing as mass of the fluid per second flowing through the tube. Okay, that is called mass flow rate. So what will be the unit of mass flow rate? It is mass per unit second, right? Per unit time. Mass per unit time, which is kilogram per second. That's the unit of mass flow rate. So what is the mathematical equation for mass flow rate? First of all, let's find the equation for mass. Then we'll talk about mass flow rate, because mass flow rate is mass per unit time. First of all, find mass, then we'll divide by time, gives you mass flow rate. So what is mass? density is mass over volume. If you multiply both sides by volume, you end up getting mass equals rho times B. So in this case, what is the volume? Let's say we consider small volume here, this much volume. This is the volume we want to consider. And this volume equals, let's say this is delta X. Then what is your V? V equals area times delta X, right? Area is area of cross section. Then rho times B is area times delta X. Okay. To find delta X, let us consider the water flows with velocity v in delta t time, such that in delta t time the water is displaced by amount delta x. Then how do you relate these three quantities? Velocity equals delta x over delta t. So if you multiply both sides by delta t, then you end up getting delta x equals b times delta t. So let's plug this in here. Rho times a is rho times a, then delta x is b times delta t. Okay, that's the formula for mass. Then how do you find the mass flow rate? Is mass per unit time, right? So that's why mass divided by delta t gives you mass per unit time, which is rho AB. That's the equation for mass flow rate. Mass flow rate is rho AB. Let us consider a tube as shown in figure. In the figure, this is end 1, this is end 2. Okay, the water or any fluid going into the tube and coming out from this end. Okay, suppose the water flows into the tube with velocity v2, where the cross-section area is A2. When it comes out of the tube, the area of the tube is A1 and it comes with the velocity V1. Okay, so then what is the mass per unit time at this end? Mass per unit time is, we know mass per unit time or mass flow is rho AV, right? So in this end, the mass per unit time or mass flow rate is rho 2 A2 B2. Similarly, in this end, we have rho 1 A1 B1. All right, now I'm in a position to define the equation of continuity, okay? The mass flow rate has the same value at every position along a tube that has single entry and a single exit for the fluid flow. That's called equation of continuity. As we did in the previous slide, the mass flow rate here is this, and mass flow rate here is this, right? They should be equal to each other. That makes sense because whatever comes in should go out, okay? So that's why mass flow rate are equal to each other at this end and this end. This is called equation of continuity. So now I'm going to apply equation of continuity in the case where fluid is incompressible. So what is incompressible fluid? Meaning density here, rho 2 is equal to density here, rho 1. If this is water, density here is 1000 kilogram per meter cubed. Here 1000 kilogram per meter cubed. That's the density of water, and whatever the point be, point 1 or point 2, the density is same. So in that case, the fluid is said to be incompressible. Okay. So if the fluid can be compressed, meaning the volume can be made smaller, right? So in that case, rho, which is defined by m over v, when the volume becomes smaller, then density becomes bigger. If the fluid is incompressible, then the density does not change. In that case, this rho 1 equal to rho 2. Okay, let's say rho 1 equal to rho 2 equals simply rho. If you divide both sides by rho, then this cancel out. Then you have the simplified version of equation of continuity, which is A1 B1 equals A2 B2. Area times velocity is constant. Okay, in other words, AB equals constant. That's the simplified version of equation of continuity, which is applied for incompressible fluid. Okay, by the way, this A times B is also called volume flow rate. What is this called? Volume flow rate. Okay, this is called mass flow rate. Mass flow rate equals rho AV, and volume flow rate is called A times B. Okay, so volume flow rate can be denoted by BQ. Okay, so why is this A times V called volume flow rate? Let's do the dimensional analysis, right? If you do the dimensional analysis, what is the unit of A? Meter squared. Then what is the unit of V? Meter per second. Then what did you get? You got m cube over, yes, which is volume per second. That's why this is called volume flow rate. Okay, let's do a couple of problems, then we are done with this chapter. Okay, so first one is blood is flowing through an artery of radius 2 millimeter at a rate of this. Determine the flow rate and volume that passes through the artery in a period of 30 seconds. First of all, we need to find the flow rate. So what is the flow rate? Q equals AV, right? So A is the pi r squared, then V is velocity. Remember, this artery is this artery. When I say A, I'm talking about the cross-section area A here, okay? So which is circle, right? So pi r squared. Pi r is 2 millimeter. Now we gotta change that into a centimeter because I wanna do it in centimeter. So 2 over 10, right? Which is 0.2 squared. Then what is V? 40. So if you do that, you will get 5.03 cm cubed per second. Okay, part one is done. Then we have to find the volume that passes through the artery in a period of 30 seconds. So this is volume per second, right? This is Q, volume, this is volume. Okay, remember, this is velocity, this is volume. So we need to find the volume. It means if you multiply both sides by T, you get this cancel out. It means V equals Q times T, right? What is Q? We figured out this is Q, 5.03 times T. We are given here 30 seconds. If you multiply them together, you get 151 cm cubed. Remember, our unit is centimeter, right? That's why you have centimeter cubed here. Okay. Okay, let's do another problem here. A garden hose. A garden hose has an unobstructed opening like this with a cross-section area of this. Okay. It fills a bucket with a volume of this many meter cubed in 30 seconds. Now find the speed of the water that lifts the hose through A, unobstructed opening like here, and B, an obstructed opening. How do you obstruct it? With half as much area, meaning you just obstruct half and only half is available here. Okay, let's do that problem. So first of all, let's find the velocity in this case, then we'll figure out the velocity here. Okay, what is the velocity here? We know Q equals A times V, right? So is Q given? Q is, the volume is given, time is given. Then Q is volume over time. Okay, A times V. Is A given? A is given also. So then how do you find the V? Divide both sides by A, you get V, right? V equals big V, which is volume, over A times T. Let's plug in the value of V. 8 10 to the negative 3. What is the area? Area is this much here, 2.85, 10 to the negative 4. Then time T is 30 seconds, right? Okay, if you do this calculation, you get V equals 0.936 meter per second. That's the velocity right here. Okay, let me call this is 1. That's why this is B1. Okay, B1 equals this. All right. Then let's figure out the velocity here, V2. So for that, we use equation of continuity, right? So A1, E1 equals A2, V2. So if you divide both sides by A2, what do you get? You got V2, right? V2 equals A1 over A2 times V1. We know V1. What is your V1? We have that here, 0.936. Okay. We don't know A1 and A2. V1 is 0.936, right? Then, oh, we don't need to, well, yeah, we know A1 and A2 because A1 is, oh, we need just the ratio of A1 and A2 because, you know, if this is 1, this is 1/2, right? So A2 is 1/2, meaning you got the ratio is, if A1, let's say A1 is, what is your A1? A1 is 2.8, 5 10 to the negative 4. Then A2 will be this guy divided by 2, right? A1 over 2. So A1 is A1, A2 is A1 over 2. Okay, 0.936. And this cancel out, this 2 goes to the top. So 2 times 0.936. This gives you the value 1.87 meter per second. Okay, so this is how you use the equation of continuity to solve the problem. Now I have a couple of more, then I'm done. All right, so we have a major artery with a cross-section area of this branches into 18 smaller arteries. So we have an artery here. It branches into 18. So there are 18 of them. This is 1, this is 2, dot, 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 18. Okay. So each with average cross section. So each of them has the cross section area of 0.4 cm squared. By what factor is the average velocity of the blood reduced when it passes into this artery? So meaning we need to just figure out the ratio of the velocity. Okay. All right, so let's use the equation of continuity here. A1 V1 equals A2 V2, right? So what is your A1? A1 is this much. Let's do this in CGS system, right? I don't want to convert this to meter. If you want, you could, but it's easy for me because I want to make sure everything is in cm. Here, this is cm. So I have to keep that in mind. So A1 is A1. V1 is V1. What is A2? A2 is, there are 18 of them, right? So this is your A1 here. This is your A2. Okay. So A2, there are 18 of them. So each of them has 0.4. So 18 times 0.4. That's your A2. Then you need to find the velocity V2. Okay. So you have the A1 also, right? A1 is 1. So 1. So what is your V2 then? So it means, see, by what factor is the average velocity of the blood reduced? You need to find the V2 in terms of V1. So if you divide both sides by 18, 0.4, 18, 0.4. Then you got B2, right? So B2 equals 1 over 18 times 0.4, which is equal to 0.139 V1. Okay. So by what factor is the average velocity of the blood reduced? So this, okay. All right. So this equation of continuity is very powerful. All right. This is the last question, then I'm done. So as blood passes through the capillary bed in an organ, the capillaries join to form venules, small veins. So there are capillaries here, lots of capillaries. Okay, they join to form venules. Okay, if the blood speed increases by a factor of 4, and the total cross-section area of the venules is this. Okay, we are given the A2. This is your A1. We don't know A1, but we know A2. Okay, what is your A2? 10 cm squared. All right. So what is the total cross-section area of the capillaries? So you have to find A1. So what is the formula? We use A1 V1 equals A2 V2, right? So what is your A1? We don't know, so we just divide this by V1, then it is cancel out. You got A1 equals A2 V2 over V1. So we know A2 is 10 V2 over V1. So but if the blood speed increases by a factor of 4, meaning your V2 over V1 is 4. Okay, so 10 times 4, which is 40 cm. Oops, cm squared. Okay, remember our unit is cm. Okay, we haven't converted that to meter, right? That's why this is the A1. Part A is done. Now, how many capillaries are involved in their average diameter? How many capillaries are involved if their average diameter is this micrometer? So how many capillaries are here? That's what you need to figure out. So A1 equals NA, meaning let's say area of each of them is A, then how many of them are there? N. We know A, how? Pi d square over 4. Okay, we know the average diameter, which is 10 micrometer. Okay, we know the diameter here. If you know the diameter, then you can find the area by using this formula. Okay, or if you want to use a radius, you have to use pi r square, right? Okay, so if the diameter is 10, what is the radius? Pi 5 10 to the minus 4, right? This is how you convert your micro to centimeter. Okay, this is how you do it. Then you just A1 is 40, as you know here. Then N is, we need to figure out, A is here, 5 times 5 10 to the negative 4. Then if you divide both sides by pi 5 10 minus 4, pi 5 10 minus 4, got this cancelled out, then your N is 40 over 5 times this much. If you calculate that, you get N equals 509 10 to the 7. Oh my God, this many. Okay, so with this I want to conclude this lecture. Thank you so much.